In this video, we're going to look at the fundamental counting principle, which ties in with probability, and it's probably one of the more fun sections because it really gets us thinking. It's almost like brain teasers that we'll get in our exam paper, and we just need to think logically and sometimes a little bit outside the box in order to solve these things. Okay, but let's have a look at the foundation of it just to make sure that we understand. And then from there, we will build and look at some typical exam type questions. So over here, we are given the digits from 0 to 9. And then it says here, the digits above are arranged to create a 4-digit PIN code. How many codes can be created if digits are allowed to be repeated? Now, this is the kind of lingo that we're going to get good at looking out for. But essentially what we want to do is we want to say, okay, I'm creating a code, and there are 4 places that can be filled in my PIN code. Now, if we take a moment to think about it logically, we can see that we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digits. And so basically this first number here could be any one of those 10 digits. So I've got 10 options when it comes to filling position 1. Then in the second one, they've said to me I'm allowed to repeat. So basically it could be any of these. Sometimes they're going to say we're not allowed to repeat, and then I'd have to consider the fact that one number would be used. But let's just ease our way into this. So again, I could take any of these 10, and I could say, well, I've got 10 options for the second place, and I've got 10 options for the third place, and 10 options for the fourth place. And so in order to say to them how many codes I could create, it's 10 to the power of 4. Okay, and so that's the foundation of it, is to say, well, if there are 10 options here, 10 options here, and you could really play around and go, okay, 0, 1, 2, 3 would be one of the codes, 0, 2, 3, 4 could be another code, etc., etc. But essentially it would take you a very long time to get to this large number here, because 10 to the 4 is actually 10,000. So there are 10,000 PIN codes that we can create just from using these numbers here. Okay, but that's when we are allowed to repeat. Let's have a look at another example. Over here we've been given 4 tennis balls. Okay, and they're all different colors, and we need to arrange these 4. So if I decide to use the red tennis ball first, then I've only got 3 options for what I could use next. So I could have 4 choices here in the first place, but once the red one is out, then I've only got 1, 2, 3 left. And so let's say I choose to use the yellow tennis ball next. So there were 3 choices there, but now the yellow one is gone, so that leaves only 1, 2. Okay, and then I could use the blue one next, even though I had 2 options there. Let's say I chose the blue one, and then finally I'm left with literally 1, and that's that turquoise color, and so that would have to be my last option. So this is a little bit different because there can't be a repetition, because each ball is allocated a place, and there are not multiple to choose from. There's 1 of each color. And so when you notice something that goes multiplying like this in descending order, then that's a very cool thing called factorial. So you could rewrite this as 4 exclamation mark, and that means 4 times 3 times 2 times 1. Now there's even a factorial button on the calculator. So if you go shift and then this x to the minus 1, you'll see above that is x exclamation mark. And so that's how we'd work out factorial. Okay, if ever you saw it, you could pretty much interpret it now. So if I gave you 100 exclamation mark, what that means is 100 times 99 times 98 times 97, etc., all the way until we multiply by 1. So that's factorial notation, very important in this fundamental counting principle. Okay, so if we are not allowed to repeat, that's when we would use this notation. Otherwise, if we had an unlimited number of tennis balls, we could have said 4 to the power of 4, because we would have had enough to create the pattern. Let's have a look at this example from one of the past papers a couple of years ago. It says 7 different cars, of which 3 are silver, are to be parked in a straight line. In how many different ways can all the cars be parked? Okay, so what we've got is 7 cars. Once we've parked one of the cars, then we only have 6 cars left to park, right? And once we park 2 cars, we only have 5 cars left to park. So that's nice and straightforward. There are 7 factorial ways of doing that, and then we can do that on our calculator. So 7, shift that x to the minus 1 button, and that tells us there are 5,040 different ways that these cars can be parked. Okay, now it says if the 3 silver cars, because they did tell us here, 3 are silver, if they must be parked next to each other, in how many different ways can the cars be parked? Okay, so let's have a look at what we are dealing with for question 2. We have got 1, 2, 3, 4, 5, 6, 7 cars that need to be parked. Okay, let's make allowance for the fact that the 3 silver cars need to all go here. Okay, silver 1, silver 2, silver 3. The thing is, they could also have a bit of an order between themselves. So this situation here is going to be a 3 factorial situation, because you've got 3 silver cars to park in the first position, and then you've got 2 silver cars and 1 silver car left to park. Okay, so there's a bit of a combo. And now we don't know where these will go. So generally when they say we want to repeat things, we start to treat this as one item. But in this case, because they are different cars, we had to really think out of the box here. And so these silver cars could come first. We could have 1 car and then them. We could have 2 cars and then the silver cars. So they form part of our options now, just in terms of allocating. So silver cars, 1, 2, 3, 4, 5. So in order to work out how many different ways we can arrange these cars so that we still have all the silvers together, we're going to have 5 factorial options for how to park the cars, but then we're multiplying that by the 3 factorial, because within those silver cars there are still some options. And then we're going to type that into the calculator. So 5 shift factorial multiplied by 3 shift factorial. You're also welcome to just work out 5 times 4 times 3, etc. But it is up to you. So 720 different ways that we could arrange those cars and still keep the silver cars together. I'm always amazed at how many options there are for these answers. It's quite incredible to think that someone sat and worked them all out. Okay, and now let's link this fundamental counting principle with our knowledge of probability. And this type of question is common, especially if you attend an IEB school. So they'll say something like this: consider the words onboard tutor. So we've got a whole load of letters to work with. And now they say how many words can be created from the letters above. All right. So they haven't specified that we're not allowed to repeat. So let's quickly calculate how many letters we have, or not calculate, just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 letters that we are working with there. Okay, so how many words can be created? In other words, how many elements are going to be in our set in total? Okay, we've got 12 over here, and once I've used the letter, it's gone. So this is going to be factorial notation. It's not like I've got unlimited letters. Okay, so 12 factorial different ways that we can create words from these letters. Let's calculate that. Okay, so more than 479 million words. They won't all make sense. That's why I've said words in inverted commas here. They don't all make sense as words, but we could, with 12 letters, we could really create a whole load of different combinations there. Now, they say, what is the probability that N and B will be next to each other? So there they are, currently next to each other. There are no other N's or other B's. So generally what I was saying earlier is then that gets treated as one element in the set. Okay, but again, important to remember that that can be arranged either as NB or as BN. So all the things we need to think about, and the best way to get good at this is just to practice a whole load of questions. But what we do then is we treat these as just one element in the set. So instead of there being 12 options now, we're going to say, well, these two are together, so we're going to count them as one option. So the number of elements in this event are going to be 11 factorial, but then be careful. It's either NB or BN. So we're also going to multiply that then by the 2 factorial option that we've got there. Okay, so pop that on the calculator. 11 shift factorial multiplied by 2 shift factorial gives us, another huge answer. 79,833,600. Okay, but be careful not to stop there. The question asked for the probability. So what is the probability? That's when we take, so probability of this thing actually happening, this event, is when we take this answer that we got, 79,833,600, divided by the total number of outcomes that there were. And that gives us a simplified fraction of 1 over 6, or if we need to give a decimal, then 0,17. Just read the instructions carefully because they differ from question to question. Okay, now, what is the probability, again, probability, that a word will not start with O-O-O? Okay, so let's have a look here. We have got a whole lot of O's in this word, in these words on board shooter. 1, 2, 3 O's in this. So basically they don't want them to all be together. Now there are going to be just too many ways to work it out. So always remember that when they use the word not, we can say 1 minus the probability of actually having all of those O's together. And that's definitely going to be an easier way to work it out. Okay, so 1 minus, now the probability. We know that we had 12 factorial in total, okay? The 3 O's are going to go at the beginning of the word, and they, remember, have their own different options as to which position they could be in. So 3 factorial. Then we will be left with how many places that need to be filled. 1, 2, 3, 4, 5, 6, 7, 8, 9. So times by 9 factorial. Let's calculate that. That gives me an answer of 219 over 220, which, if they want the decimals, is very, very high. 0,995. Let's give 3 decimal places there, otherwise we end up with 1. And then finally, how many different words can be created? So in other words, what they're saying to us is they don't want repetition. If letters repeat, then we end up with, on board and on board. But the difference is here, this O moved to position 4, and this 4th O came to the first position, and it looks like the exact same word. So what they're trying to do is avoid that. So we need to now try and figure out how many duplicates we've got. So if we look at these words, we'll see we've got O times 3, we've got R times 2, and we've got T times 2. We've got some duplicates that we need to deal with. If we want to have different words, this is how you approach it. You can work it out by taking this formula here. Let me explain it to you. So we've got the number of elements in the set. Above the fraction here, or in the numerator, we've got the total number of elements. So we have 12 different letters, or 12 letters altogether. And then here we want to divide by the duplicate factorials, because remember, there are 3 different ways the O's can be arranged, 2 different ways the R's can be arranged, 2 different ways the T's can be arranged. That would lead to duplicates. So I would then substitute, and I would say, okay, well, 12 factorial were my total number of options, divided by 3 factorial for the O's, 2 factorial for the R's, and 2 factorial for the T's. And so without having to do too much thinking or stressing, I can just type that into my calculator and come to an answer. So if ever you get asked something like this and you need to know how many different permutations you can create without having any repetition, you need to apply this formula here. And it's not bad as long as you remember in the numerator is the total number of words that you can create, and in the denominator you want to divide by the number of repetitions that each of the letters presents.